All right, the subject of this slide set is multiple regression, and this is really where we get into the thick of it here, where we can start developing some pretty useful models from the standpoint of business analytics. So up until now, we've stayed in the realm of simple linear regression where we tried to predict y from a single predictor variable, like predicting college GPA from ACT score. Now, for most data sets, we're going to have a lot of different variables that have been recorded, and so there's no reason to restrict ourselves in predicting y from just one predictor variable. We want to incorporate information from all the variables that we've collected. So multiple regression is going to allow us to do that. We're going to be able to predict y from numerous different potential predictor variables. So let's start out with a little bit of a motivation, and let's go to a data set that we've spent a lot of time talking about, the salary data set, where we have about 80 or 90 employees at a company, and we've studied how the salary every month varies versus the employee's number of years of education post-high school, the amount of years of experience they had before getting hired, and the number of months that they had already spent at the company. And looking at these three scatter plots, we see that each of these predictor variables looks to have a positive association with salary. So there's no sort of nonlinearity going on. And so a simple linear regression model is appropriate. When we did this, we saw that education in a simple linear regression model had a statistically significant association with salary. Its p-value is less than 5%. And its coefficient was 85. The slope of that line in this previous slide was 85. And so what that meant was that two employees that differ in education by 1 year are expected to differ in their monthly salaries by $85, with the more educated employee having the higher salary on average. One thing that we also saw was that experience did not have a statistically significant relationship with salary. The p-value is 11% here, bigger than 5%, so it doesn't look like that salary can be predicted from experience any better than predicting salary from just some random unrelated predictor. We also saw that months was a statistically significant predictor since its p-value is 0.5%, less than 5% here. However, there may be more to the story because if you think about it, we probably already know what predictors really matter when determining salary. And definitely experience really does matter. It's unlikely that someone who gets hired with 15 years of prior experience is going to have the same average salary as someone who has no experience. So we need to do a bit of further investigation here. So it might be the case, actually, that the effect of experience on salary could be overshadowed by the effect of education. And so let's imagine the following scenario to illustrate why this might happen here. Imagine that hiring policy actually has an equation that relates the monthly salary to the amount of education and the amount of experience the employee has. And let's imagine this is the correct equation. Basically, we take the years of education multiplied by 1,000 and then add in 10 times the number of years of prior experience. So the truth is that yes, experience really does help to predict salary. And let's run a simulation to actually see why our simple linear regression might actually conclude otherwise, that there's no significant relationship between salary and experience. So basically what's going to go on is that what we see in this equation is that the effect of education looks to be a lot bigger than the effect of experience. You know, an additional year of education essentially buys you an additional $1,000 of salary, whereas an additional year of experience only buys you an additional $10 in salary. So most of the variation in salary is really due to differences in education between employees. Only a small variation in salary is really due to differences in experience. And so let's see what happens when we run a simulation here. So I'm going to set up the random number generator in a specific way with set seed, and I'm going to randomly generate educational values for the 50 employees in my mock data set, and I'm going to randomly generate 50 random experience values for the employees as well. The average value of education is 4, the average value of experience is 6, with a standard deviation of 1.5 and 2, respectively. Okay, so let's use the equation that the hiring committee is actually using. Salary is equal to 1,000 times education plus, in this case, I'm going to bump up the effective experience just a little bit more, 100 times experience plus a disturbance here. Individuals aren't ever going to exactly equal the average. The disturbance is a little bit of a bump up or below the average salary to account for individual variation here. All right, so we've generated our employees' educational and experience levels. We've designed what their salary is. We know that the truth is that the coefficient of education is 1,000, the coefficient of experience is 100, and individuals differ from the average by about 700 or so, the standard deviation of this normal. Okay, so with this artificial data set, if we make the scatter plot between salary and these two predictors, we see that there's positive associations going on. The relationship between salary and education looks to be very strong and linear, whereas the relationship between salary and experience looks to be really quite weak. It's still sloping up, so it's a positive association, but it's a very weak, small slope. We don't see the average salary varying by all that much over the entirety of the range of experience in our data set. There's a very small change in average salary. So if we fit those simple linear regressions, say predicting salary from experience, what do we end up seeing? Well, we know that the truth is that experience really does have an effect on salary. And if we look at the p-value of experience in a simple linear regression, we get 55%. Well, that's bigger than 5%, so there's no statistically significant association going on between salary and experience. But like I was saying, that's probably due to the fact that it's getting covered up by the association between salary and education, a much stronger relationship. So we see that the simple linear regression predicting salary from education has a p-value much less than 5%, so it's very statistically significant. The estimated coefficient is right at about 1,000, which is what the truth is, so that's good news. So I was saying education has such a strong effect on salary that the effective experience essentially gets drowned out. So let's do something to try to flesh out the effective experience. Let's actually take the values of people's salary and then subtract off what the predicted salaries are from a linear regression using education as the predictor. So basically, salary minus the predicted values are just the residuals of the salary. It's basically what's left over of the employee's salary after we've accounted for someone's educational level. And so let's try predicting this leftover salary from experience. Well, if we do that, we find that, yes, there is a statistically significant association going on between the experience someone has and the amount of salary they have that's left unaccounted for by education. And in fact, the coefficient is right about the truth. The truth is 100. What we're estimating is 116 here. So in the end, we actually do figure out that, yes, experience does seem to matter when determining salary, but we were only able to stumble upon that after we accounted for the effect of education. And so that's going to be one of the goals of multiple regression. We're going to add in a bunch of predictors in our model because in order to really isolate the association between y and a predictor variable, we may need to first account for the variation in y that's due to other predictors. So we take away those extraneous factors of variation, and then we can much better glimpse the association between y and our x of interest. So here's a scatter plot representing what we just talked about. Salary and experience just by itself has a very weak positive association that we saw was not statistically significant. But if we look at the leftover salary that's not accounted for by someone's education, we see a much stronger association between that and experience. In fact, it was statistically significant. All right, another example exploring multiple regression from a different viewpoint. It turns out, and it's pretty well known and well documented, that some ethnic minorities tend to have lower high school GPAs and lower college GPAs than Caucasians. So this is an interesting observation. It has fueled substantial debate, and it's been motivation for many completely unfounded racist remarks and arguments. And so here's actually where multiple regression is going to be useful for us. It turns out that when we study the association between y and x, it's also important to take into account other variables that are related to our predictor variable of interest, related to x, even when they may or may not be directly related to y itself. So to illustrate this, let's imagine the following hypothetical argument, that race really does have no inherent direct connection with GPA. So every race is capable of getting the same GPA. Let's assume that's the truth, and it probably is. And let's imagine that what actually does affect GPA is the consumption of a particular food. Maybe this particular type of fish is brain food, and consuming it actually helps you to do better in school. And so the consumption of food A really does have a direct connection to GPAs. Okay, so let's imagine, just for the sake of illustration, that Caucasians are actually the race that predominantly eat food A, while ethnic minorities just tend to not eat food A for whatever reason. Well, okay, what we're going to see as the result is that there will be a variation in GPAs, but the variation in GPA between races is not going to be due to race itself, but rather differences due to diet. So it's not that Caucasians are inherently better at school and are going to get better GPAs than ethnic minorities. What's really going on in this hypothetical example is that Caucasians happen to eat more of food A, and it turns out that food A, for whatever reason, makes you do better at college, makes you get a higher college GPA. So if we really want to study the association between college GPA and race, we first need to take into account the dietary consumptions of the races. We need to account for an additional variable. So, in general, and this is what multiple regression is going to help us out with, when there are many different potential predictor variables, many different x's, that could be responsible for the variation in individuals' y values, you can't fully examine the association between y and a particular predictor variable with a simple linear regression, because the simple linear regression doesn't account for any sort of extraneous variation in y due to other factors. But multiple regression is going to allow us to correct for this. Multiple regression allows us to account for other variables in order to isolate the association between y and x. So this is incredibly useful. If we really want to study the association between, say, salary and experience, we also need to account for education, amount of months on the job, any other factors that might also be responsible for variation in salary. If we really want to study the association between GPA and race, we also need to take into account other factors that might influence GPA. Socioeconomic conditions, diet, parental involvement, anything else that might also be responsible for variations in GPA. Likewise, if we want to study the association between, say, obesity and heart disease, well, we really have our work cut out for us, because there might be a lot of other factors that go into kind of causing heart disease. And in our regression model, if we really want to study the association between obesity and heart disease, we need to take into account all these other factors like diet, exercise routine, geographic location, etc. But once we've done that, once we've accounted for all the extraneous sources of variation, multiple regression allows us to really isolate the association between y and our predictor of interest. All right, so here's what the multiple regression model is trying to do. It's trying to predict y from a whole bunch of different predictor variables. It looks just like our simple linear regression equation, but we've just added in a whole bunch of other predictors in the model. A total of k different predictors, each of which has their own coefficient, plus a little bit of disturbance to represent that individuals are kind of randomly above or below the overall average. And so just like with simple linear regression, there are a few assumptions that go behind the model. Number one, we assume that the average value of y varies linearly with each predictor variable. So if we were to make a scatter plot between y and each of these predictors, we'd see a nice linear relationship. And also, like simple linear regression, we have this normality assumption of the disturbances that basically tells us, okay, the typical difference between an individual's y value and the overall average at that combination of x's should be about the same regardless of its x value. So individuals deviate from the average by about the same amount, no matter what the characteristics of that individual is. And not only that, not only do they deviate by the same typical amount, but the possible deviations that they can experience is in accordance with the normal distribution, nice and bell-shaped here. So this is what the multiple regression model is doing. It's adding in just a whole bunch of other predictors into the regression model. And if we're really interested in studying the association between y and x1, well, including x2, x3, etc. into the model is going to allow us to account for the variation in y due to these other factors in order for us to really isolate the association between y and x1 here. So, all right, the first step really in any sort of analysis is to make sure that this model looks to be appropriate, and we need to look at plots. And since there's so many predictors, we just don't want to look at one scatter plot, we want to look at the scatterplot matrix. So if you remember, the scatterplot matrix gives you the scatter plots between every single pair of variables in the data set. You can use the pairs function in R to produce that. And the syntax is just like with the LM syntax here. So basically y is on the left, then a twiddle, and then all your x variables that you want to look at separated by plus signs. So here's the scatterplot matrix of the salary data set, and we see that, okay, salary is up here at the top. These three scatter plots show that there's a roughly linear relationship between salary and our three potential predictor variables. The census data set is something we've also talked about, trying to predict the fraction of households that respond to the census form when it's actually due. And in this case, there's so many different variables that actually typing out every single variable separated by a plus sign is inefficient. R has a shortcut that says, okay, if you do twiddle and then a dot, that implies, okay, I want to use every single variable in my data frame. So male return rate twiddle dot is going to make the scatterplot matrix showing how the male return rate varies with every predictor in this data set. And in this case, there's so many predictors that we really can't quite tell what's going on. So actually going into RStudio and making this scatterplot matrix, here we see it. It's really hard to see what's going on. We can always click zoom to get an idea of what's going on, and we can resize the plot a little bit. So we can look to see, okay, how does the male return rate really change with all these other predictor variables? And it looks roughly linear. It looks like this would be a good candidate for a multiple regression. But if you're faced with a very large data set, say like the NFL data set, which had hundreds of predictors, we can actually isolate and make a scatterplot matrix of just a subset of predictors if we specify the columns of interest. So instead of saying, okay, pairs, y twiddle dot, we can actually say let's do pairs and then specify the columns that we actually want to have scatter plots for. So in this case, the very first column was male return rate, so I specify that first. And imagine we wanted to study the association between male return rate and age. Well, it turned out the 4th, 5th, 6th, 7th columns of the data set are the age characteristics. And so we can just say, well, let's look at it just with these particular columns. So we have in square brackets a blank, and then a comma, and then a vector of the column numbers that we want. Okay, so that will conclude this little section. We'll move into talking more about the regression model, how we actually get the coefficients out, how we interpret them, etc. in the next section.